Now recall that we called map F from a group G1 to a group G2 an isomorphism if it preserved the operations, or it respected the operations and the group operations we meant, and in addition it was one onto or bijection. Now let's do this. Let's remove this condition, okay? And then if say by the bijection condition is not satisfied, only the operations are preserved, then what do we do is we call it a homomorphism between the two groups, okay? So we drop extra requirements and get another definition. Now you shall see that even with this preservation property, we shall see, or we shall find, many interesting features. And before we go towards those, why don't we look at some examples? Now it'll be easier to to consider an example. For instance, if I have any group G1 and any group G2, I can do this. That is, define the f of x, and of course is an element from G1 equals E2. That is the identity in the group 2, the identity, okay, in the group, or in simply G2. And here, of course, this will satisfy this property, and for any A and B in G, and I did not write here that for every A and B in G1, but that's what I mean. Let me just go ahead and do that. So I'll just write for every A, B in G1. Now change the symbol. Let me just make it like normal. Okay. So for every AB belonging to G1. Okay. So sorry, I'm having trouble finding fonts here. Okay. So in here, what we have, this also holds for what? For every x in G1, right? So if we have, say if we got this here, f of AOB, now this may be treated as x, right? If we take x to be A times B via the operation in G1, then who the image will be? That will still be E2, the identity, because for any x in G1, it's going to E2. And who is E2? I have to look for this now, right, to fulfill this condition. So what we would do is we'll take E2 and then take the operation and multiply that again with E2, because we know that both, A times B goes to E2, A itself goes to E2, right? Because, so what will this mean? FA as well as FB will be E2, no matter, who A, B, and the other elements are, right? Okay, so I hope I'm not just going too slow or over explaining it. All right, so you can see in this manner that this is this, so this becomes, what does this become? This will become in this manner, F A times, and times will come in from G2, okay, FA times FB, because each of them is E2, okay, all right. So this is the homomorphism, a very simple one, okay. Now let's just go ahead and look at some other examples of homomorphisms, and right now we will look at the ones that are not one-one onto, or that are not bijective, because the ones that are, we have seen those before when we took isomorphism, okay. So in the similar manner, I can take a map from R star to R star is the non-zero reals, R superscript plus is the positive reals, both of them with respect to the multiplication of real numbers. And if I define the map by this definition, that it just goes to a square, you can see that for any two real numbers, what will happen? Xy will go to the square of xy, and you can see this, that here power of a product is product of the powers, right? So we will get fx times fy, and the homomorphism condition is satisfied. And we can even take homomorphism between the same two groups in a different manner, like take it as absolute value of x, and you can see that the condition is will be satisfied in the same way, because the absolute value of a product is the product of the absolute values. And for example 4, yeah, let's just take another example, say example 4. What we shall do is, we will take, or we may take, f a map from the additive group of real numbers, all right, okay, to say the multiplicative group of non-zero complex numbers, okay. And we may do this, that is, take fx to be e to the power what ix, okay. So that's what we defined the map to be, okay. And in this case, what will happen if I take f of say x plus y, okay, what will that be? E to the power I, then x plus y, right? And this is going to be e to the ix plus iy, and that will become a product, just knowing the nature of these exponents, right? Okay, so this will be e to the ix times e to the iy, and that's going to be fx times fy, and that will of course be a homomorphism from the additive group of reals. And here the operation is the addition of numbers, and here it is the multiplication of complex numbers, okay. And so I'm just narrating examples in this manner. Let's just take another one, which is example 5, we'll say. So here, why don't we take it from, f from, I'm just thinking out loud here, okay. And so we are going from, say, z2, what? Let's take z modulo. I can take any number. I'm just choosing to take 6. Okay. So what we shall do here is our map will go like that. Fx goes to the value x mod 6. So for example, say I have to write f of 11, what that will be, just use the division algorithm. The quotient is 1, the remainder is 5. So f11 is 5 because that's what 11 mod 6 is, right? Okay, so that equals, or let me just write it a little more explicitly. That's 5. And here the number on the right hand side is an element of Z6, right? And here what happened, let's take just another one just for fun. Okay, let's take, say, for example, 74. So 74, if I divide 74 by 6, what will I get? 12 times 6 plus 2. 2 will be my remainder, right? So that will be 74 mod 6, that is 2, right? And say, for that matter, say I took negative 3 here, okay? Now, if I divide negative 3 by 6, what do I need? I mean, I have to have a non-negative remainder. So how are we going to get it? Let's just recall the process. So since the remainder has to be positive, what we can do is that we can write negative 6, negative 3 as, so here, we took negative 1 as quotient and 3 is the remainder. So that's a 3. And that is in case you are taking Z6 to be the set of elements, okay, between what? 0 and 5. And they're all just mod 6 for the sake of clarity of expression, okay? And here that if I took a sum of two integers, okay, then the x plus y mod 6 is going to be, sorry about that, xy plus y mod 6 would be simply x mod 6 plus y mod 6, right? Okay, and that will make it a homomorphism because who those guys are? They are fx plus fy, right? Okay, f of x plus f of y. Okay, so and this is just because of this property. We did not prove it like in a routine way, but we had adopted it from our book, right? And again, what do we mean by the book? Abstract Algebra, okay, Theory and Applications by Thomas Judson, okay? So by Thomas Judson. And let's take just a different type of example again, just for having a variety. So we got Z to Z6. So we have example 5, then example 6. Remember this, if you recall that you take what is called GL sub 2R, okay? Who is that? That's the group of 2 by 2 matrices with real number entries whose determinant is what? Whose determinant is not equal to 0, right? Okay, so you can take map from this group, which is also called a general linear group, okay, to R star, the group of non-zero real numbers, are defined by f of uh, matrix A, which is a 2 by 2 matrix A that equals the determinant of A. And, since what happens is if I take two square matrices, and here we are just looking at 2 by 2 matrices, product of their, determinant of a product is product of the determinant. So this is going to show you easily that this mapping is a homomorphism. Now say you did this, for example, say I made a change in one of the examples that we had, say, this one, okay? So say I changed it to this here, that is fx equals, say, 2x square. All right, okay. And again, by superscript positive, we simply meant positive real numbers. I didn't have to, it could even be taken as a map from R star to R star, okay. But the problem here would be this, that fx of y, sorry, f of xy is going to be what? 2 times xy squared, right? And so when we write it out, it will be 2x squared and then times y squared. So here, this part is f of x, but this is not f of y, right? So what happens here is that we find that this is not equal to f of x times f of y. So therefore, this is not a group homomorphism. Okay, so here are just some basic examples, and this is a basic course, so we'll stay with the basic examples. So let's just go towards some properties of homomorphism. Okay, and many of the properties that isomorphism satisfied, not all of them of course, because here we may not have bijection, are satisfied by homomorphism also. Let me just show you the appropriate page from the book. So here on page 193, you can see that if I have a group homomorphism, then identity is carried to identity, inverse is carried to inverse, a subgroup is carried to a subgroup, and at the same time, a subgroup of G2 is pulled back into a subgroup of G1, all right? And the same for normal subgroup. So it's just like the way we worked in isomorphism. The book does a nice job of proving this. Actually, the book does the good job of proving all the theorems, but let's just prove about two results in the time that we want to allow to this topic. Now let's take up something that we did not take up when we did the isomorphism, that is the kernel of this kernel of a homomorphism F. Let me just write that as just a simple word, because I think kernel, I mean, in English, it means, the very essence of something. So it will be essence of a homomorphism in many sense. And for isomorphism also, it tells us an important property. So let's just take it, let's just write the definition of kernel, or what the kernel is. Okay, and just for short, let's write it as simply kernel of X, KERF rather. Okay, so what it does is it contains all those elements of G1, okay, or the group that is forming the domain, okay, that are mapped into the identity, okay. So identity of the group 2, and let's not worry about writing it as E2 because we had that later on. We will just have our symbols generally self-explanatory. So when we say fx equals E, that means the identity in G2, okay. So this, of course, is a subset of G1, okay? And you can easily see that this is not only a subset of G1, it will also be a subgroup of G1, okay? So kernel of F is a subgroup of G1. And what do we have to do to show that? Remember? That is, all we have to do is, if we have A and B in the kernel or in this subset, right, then we have to show that AB inverse is in there as well. So let's just go for it. This means that FA equals FB, and both of them are equal to the identity in G2. Now, AB inverse, remember this, that yeah, that's what we have to do. So AB inverse is going to be in the kernel. And again, just to remind you of the property, if we can show that for AB in kernel of F, we have AB inverse also in kernel of F, then kernel of F will be a subgroup of G1, right? So what will be the qualification for this to be, uh, uh, to be in the kernel of F? It will be this, that the F of this element should be the identity, right? So which means what? F of A, right, times F of A B inverse, okay? Or let's actually, we have to show that, so it will be better, okay, yes, to rewrite it, okay? So let's just rewrite it so that to check if this is satisfied. So why we are doing it this way? Because this will mean AB inverse is in the kernel, and then the kernel is a subgroup. So let's look at this. F of AB inverse, where that indeed is the kernel, so that is going to be F of A times F of B inverse, right? Okay, now we know this, that F of A and F of B, both of them are equal to E. So one part is simple. We get EFB inverse, right? Which is F of B inverse. And remember this, that we just saw from our book that under homomorphism, inverse is carried into inverse, right? Which in our case will mean that we have, this will be F of B inverse, right? And F of B is who? That's identity. So we get what? That equals the identity inverse, and inverse of the identity is identity. So this whole thing becomes simply E, which means that AB inverse, that belongs to the kernel, right? And which means that the kernel of F is a subgroup, right? And likewise, we can also extend it to this statement that it's not only a subgroup, it also gives us, in addition to being a subgroup, okay, this is a normal subgroup of G1, okay, normal subgroup of G1. So how can we check that? Remember this, one of the criteria was that if we can show this, that G inverse, okay, Kg, that belongs to the kernel of F, right, for all G in G, right, for all little g in G, and for all k in the kernel, right? Okay, so k in the kernel of F. So that gives us this as a normal subgroup. Sorry, that will give that as a normal subgroup. Okay, now, so this is what we want to check. Now, when will this be satisfied? If the image of this element under F is going to be what? The identity, of course, in G2, right? So let's just apply F on this. So again, using the homomorphism property, what will happen is this will become F of G inverse, then F of K, then F of what? G, right? Okay, so then notice this. F of K is identity, right? Because K is in the kernel. So what will happen now? Identity will just drop off because it doesn't matter which way we take it. This is F of G and this is F of G inverse, right? So this becomes this, right? Now we have two ways of handling that. One is this, and I think that will be easier. If you look at F of G inverse G, since this is a homomorphism, what happens is this is the same as this, or we could have gone the way we did here, that could have taken the F of G inverse as the inverse of F of G, that will produce the same result. So this is F of the identity in G1, and that will go to identity in G2 just because of the fact that F is a homomorphism, right? Okay, and a homomorphism, as we had seen, carries identity to identity. Okay, so we saw that kernel of F is a normal subgroup of G1, and remember this, that we didn't take this up for isomorphisms because if the homomorphism is an isomorphism, that is, it has one onto property, then what will happen to kernel? Let's see what will happen to kernel in that case. Okay, so let a homomorphism, excuse me, F from G1 to G2, okay, so we know this is given to be a homomorphism, right? So let this be 1, 1, okay? Okay, so let's see what will happen now. If we have X belongs to kernel of F, sorry, I took different. So if we have an element in kernel of F, what will that tell us is that fx of, you know, f of x is going to be the identity, right? And this is given to be 1, 1, right? But at the same time, also, we have f of the identity. I'm not writing them as E1, E2 anymore. That is also identity. So what does it mean? This simply means that f of x is going to be who? F of e, right? Now, we are given that f is 1, 1. So what will that give us? So if these are going to the same destination, then the two elements must be the same, okay? So what happens? If this is 1, 1, okay, then, so a homomorphism, okay, is 1, 1. What does that do is, or what it does is, that it implies that x is in kernel of f, means x is the identity, or in other words, kernel of f has only one element, that is the identity element, right? And the other way around is also true, that if, say, given that, and here is homomorphism, keep this in mind, okay, all right. So given that, let me phrase it here, given for this, that kernel of f is only the identity. Let's see if we can check, or we can see if f is going to be 1, 1. So this is what we are assuming. So what do you do for, one of the ways we check whether the function is, or whether a function is 1, 1 or not, that we assume that two elements are going to the same destination, or two inputs have the same output, okay, and then we have to show that the inputs have to be the same, or okay, so we got this, right? Now in this case, what we are doing, in a way, we are doing algebra anyways, and we are solving equations, right? And this was one of the ways of solving it, right? That is just to multiply by the inverse on both the sides, and okay, so we got everything on one side. Now, this, we have a homomorphism, right? So what will happen? First thing that will happen is this inverse, or inverse of fx2, is nothing but f of x2 inverse, right? Or in other words, what this means is that we have this thing as simply f of x2 inverse, right? Now, what will this imply? That is going to tell us that f of, I took wrong symbol, I'm so sorry. Here you go. So that will tell us that because of these guys being homomorphisms, what we can do is that we can, oh, sorry, combine them as the image of their product, right? So we have f x1 x2 inverse equals E. What will that imply? And this E is in G2. So keep that in mind, that this belongs to who? This is in the kernel of F, right? Okay. Now, if this lives in the kernel of F, then kernel of F has only one member in it. So what has to happen then? That this has to equal the identity, and then what will that mean? Now we got the relationship. We can just send x2 inverse back to right side, right? Then, sorry, we can multiply both the sides by x2. x2 times e is x2, and x2 times x2 inverse is simply the identity. So this will just come down to this. So what does this show then is that the homomorphism that we have here is 1, 1, right? So what we just did was we showed that 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 a homomorphism between two groups is 1 to 1. We showed both, the implications on both the sides. So instead of that, we just showed that if and only if the kernel of F is what? The identity. So let's just go ahead and look at the kernels in some of the examples that we took up while defining a homomorphism. Okay. So, I mean, like geometrically, here we have the group of real numbers with addition as the operation, and here we have group of non-zero complex numbers with multiplication as the operation. So what happens here is that every point just gets mapped to a point on this unit circle under under the map fx equals e to the ix, because as you can see by Euler's formula that this is cosine x plus I sine x, and if we compute the modulus, then the Pythagorean theorem gives us that cosine square x plus sine square x is 1. So all the numbers have modulus 1. So they all the images, they live on this circle. And for this f, what we got was that the kernel was the cyclic group generated by 2 pi. All right. So now let's go over the other examples. Okay. So like say here, example 5, here we had taken fx to be x modulo 6, right? So what we need is the identity in Z6 is how much? This is our homomorphism. We saw that that was a homomorphism, right? Okay, so in that case, if x is in the kernel, okay, all right, so if x is in the kernel of f, okay, then what will happen is this, that fx is going to be x mod 6, which will have to be what? Which will have to be 0, right? Okay, now who are the numbers who are 0 mod 6? They are all the multiples of 6, remember? So that means that x belongs to who? X belongs to the just the multiples of 6, or in other words, just the cyclic group generated by 6, right? Okay, so if x is in kernel of f, of course, then x will have to be a multiple of 6, and vice versa. If x is a multiple of 6, then fx as this would be 0, and again that will give us what? That x is in the kernel, right? So we have it both ways. So kernel of f is how much here? Just the cyclic subgroup of Z that is generated by who? That is generated by the powers of 6. Let's take this one also. Example 7 was not a homomorphism, but in this one, if we look at R star, okay, if we, let's just, send it downstairs. So here, the identity is how much? That's a 1, right? So what will the kernel be then? That will be the set of 2 by 2 matrices, okay, matrices, of course with real entry here, okay, with determinant 1, right? And remember what we call such matrices. If you don't remember, no big deal. Just review the notation. That is SL2R, right? That is the special linear group of 2 by 2 matrices over the real numbers. So for this function, the kernel of f will be simply what? That is special linear group. Okay, so let's see what does this kernel give to us. We know one thing, as I said, that the kernel K, okay, say if we call it K, and this is the kernel of F for a homomorphism F, okay, then it is a normal subgroup of the domain group, right? Okay, of G1, right? Where F is a homomorphism between G1 and G2. I'm writing it again because it doesn't hurt to just keep things as clear as possible. So let's see what we get from out of it. Okay, so we got this here. Okay, so now we have, say, a homomorphism between G1 and G2, and in this manner we have gotten what? We have gotten a normal subgroup of G1. So what will happen here? This would be, all the left cosets of K will form a group, right? So this will be a group, right? Okay. So let's see if we can connect G1, G2, and G by K. So let's go to a drawing board where I can write by hand. So what we have here is that we have a map from, or homomorphism from, G1 to G2. Now if we took K as kernel of F, then G1 by K is a factor group, and then a typical element in here is xk, right? And since I wrote xk, I can define a map here. Let's call it, say, f bar, that takes x to what? Xk, it's left coset, right? Okay, and here f does what? It takes x to f of x, okay? So we may think of this, that what if we define a map that takes xk to f of x? That is, let's call it phi. So what we want to see is that if we define a map phi from g factored by g1 factored by k to g2, that is defined by this. First of all, is that kind of a map possible? You know, that's first curiosity. And if it is possible, whether it is a homomorphism, whether it is 1-1, and its onto will, being onto will definitely depend upon f being onto. So that will come towards the end. So to check, what do we want to check? To check if phi is a map. All right. So how do we check it? If two elements are the same, their images should be the same, right? So these two elements are the same. Now one criteria of them being the same was, okay, you may recall, is that x1 inverse x2 is k, right? Okay, so this means f x1 inverse x2 is going to be who? The identity, and this will mean, remember this, it's a homomorphism, right? I did say but didn't write. It's a homomorphism, so we get that, right? And the inverse is taken to inverse. So this becomes f of x1 inverse times of f of x2 is identity, right? Now multiply by f of x1 on both the sides. What do you get? fx2 is fx1, or fx1 is fx2, okay? And which means phi of x1k is the same as phi of x, just a second, okay, let me write, okay, or I can write here, phi of x1k is phi of x2k. So phi is a map, all right. That answer is, of course, yes, we did realize phi is a map, right? Now, remember this, we are just addressing a curiosity that whether phi is a homomorphism. So there is a question, is phi a homomorphism? Okay, so what will we need for that? If I take x phi of xk times yk, all right, then whether that will be f of x times f of y. So let's look at that. This is phi of xyk, right? K is a normal subgroup. Remember, this is normal. I say things that I don't write, okay, of G1, right? So, and this by definition is f of xy. Now, f of xy is what? F of x times f of y, again, just by the property that this is a homomorphism, and this then, can be split that as product. So these are fairly easy reasonings, I think. I hope I'm not making them super complicated. So what we saw is that phi is a map, and it is also a homomorphism, right? So what I can do is, let me let me erase this and then we will come back to this later. We'll sketch it again because what I want to check now is whether this guy phi is 1, 1. Okay, so question is phi 1, 1, and who is phi? Phi is defined right here. So 1, 1 will mean what? If I have phi of x1k equals phi of x2k, x1 will x1 k will have to be the same as x2k. Okay, all right, let me just put this here. Okay, so what will this give us? fx1 is fx2. So I think all the arguments might be looking the same to you all. All right, so here I can take it to the other side. So that will be f of x1 inverse times f of x2. That means E equals f of x1 inverse times x2. That implies x1 x2 inverse, x1 inverse x2 is in k, and again remember that was the criteria for xk to be yk, or x1k to be yk, right, or x1k to be x2k. All right, so what did we see? We see it is 1, 1. So, of course, as I said, or as we saw, if our map f from G1 to G2, if that is an onto map, then this map phi will be an onto map as well. And what will that give you? That will give you that this factor group is isomorphic to that because it is a homomorphism, it is 1, 1, and that's an and that's onto if f is onto. So let's write this final statement now. Okay, all right. So let me erase this whole thing. Okay, and just as so, what you have is that G1 to G2. Let's take F to be an onto homomorphism. Okay, so let's this to be an onto homomorphism. Then we have F bar here, which takes us to the factor group, and this is phi. So x goes to fx here, x goes to xk, and here xk goes to fx. All right, okay, so what happens is that, and we can also see that if we go ahead and compose phi with f bar, we are simply going to get what? We are simply going to get f, all right? Okay, so this composition is true, and this phi is what? Phi is an isomorphism. So all we saw was this: if I have an onto homomorphism, I can obtain the kernel of that, which will be a normal subgroup. So that will give me a factor group. Once I get that factor group, the factor group is just going to be isomorphic to what? Isomorphic to this G2, the image of this G1 here. Okay, so this is called actually the first isomorphism theorem And as I said, about 50 years ago when I took this course, my professor called it the fundamental theorem of homomorphism. I'm sorry again about the handwriting. Handwriting is bad, typing is slow, but fortunately, we don't have to talk much anymore for this particular topic. What we can do is this, that we can just, bring some of the examples that we did, okay, and just, look at them in the light of this theorem. So one of the examples that you had done was, let me erase this, say I do this, and we already did that one. That is, say we take this thing here as, say, S1, the unit circle, that's subgroup of complex numbers, right? Then you saw just a while ago that from R and the set of positive integers, we can have a map X that goes to e to the ix. So if all that we are doing is this, that we are going from R to, say, simply S1, that is the circle group, right? Then in that case, that will be an onto map, because any point on this circle is of the form cosine theta sine theta, that can be written as this, and and the two thetas are the, and cosine theta sine theta are the same, so we can see that x can be taken as theta. All right, I'm just saying that in terms of theta, sounds a little easier there. Okay, so if we look at this map, we saw that the kernel of f was what? The cyclic group generated by 2 pi, right? So what happens here is that if you do this, if, and of course the cyclic group generated by 2 pi, and R is an abelian group with respect to plus, okay? So this is the normal subgroup, so this is the factor group, and here what we have is that this factor group is isomorphic to what? S1, okay? Or, looks like we are just wrapping it over into a circle, but let's not get that sophisticated yet. So this is one example, and an easy thing would be this. The other example that we looked, just go ahead and see what kind of isomorphisms are produced by these. Okay, so let's just stop here on this topic, and I'll see you in the next presentation. Okay.